Hi, in this video we are going to talk about this problem, count inversions in an array. Let us first define what is an inversion. A pair array I and array j is called an inversion if I is smaller than j and array I is greater than j. It means a greater element appears before a smaller element. If that happens, then we call these two elements as inversion. Let's see this example. We have an array 2, 4, 1, 3, 5 and we need to count how many inversions this array has. So one inversion in this array is 4, 1, right? One pair is 4, 1. Other inversion is 4, 3. One more inversion in this array is 2, 1. So there are 3 inversions in this array. Let's see this array. When you have an array sorted in increasing order, the number of inversions are always 0. Let's see this array. When you have an array sorted in decreasing order, the numbers of inversions are always maximum possible. In this array, we have 6 inversions. You can notice that the first element forms 3 inversions. The second element forms 2 inversions. The first element forms 3 inversions with 30, 20, 10, all of them. 40, 30 is an inversion. 40, 20 is an inversion. 40, 10 is an inversion. Similarly, second element forms inversion with these two elements. 30, 20 is an inversion. 30, 10 is an inversion. And 20 forms an inversion with this element. 20, 10 is an inversion. So in general, if your array is sorted in decreasing order, then your first element is going to form n-1 inversions. The second element is going to form n-2 inversions, and the last element is going to form 1 inversion. And the total number of inversions is going to be n into n-1 by 2. In general, when your array is sorted in decreasing order. Now, please pause this video and try to write down a function that takes an array as an argument and returns count of inversions in the array. Let us now talk about the naive solution to solve this problem. The idea is to traverse through all the elements starting from first element to second last element. For every element, we count how many elements are there on right side of it which are smaller than this element, right? And that's how we count inversions, where this particular element is the greater part of the inversion. Let's consider this array for an example. We are going to begin from the first element and are going to go on till the second last element. We are going till the second last element because for last element there won't be anything on the right side of it, right? And we need to count how many elements are there on the right side which is smaller than this element. So we begin with 2. We count how many elements are smaller. We get the count as 1, right? And this is counted by this loop. Now we come to 4. We count how many elements are smaller. We get count as 2. So our result becomes 3. Now we come to 1. We count how many elements are smaller. There are 0 elements. So our result remains 3. We come to 3. We count how many elements are smaller. There is no element which is smaller. So our result remains 3. And at the end, we return the result. Now what is the time complexity of it? We have nested loops. The outer loop runs from 0 to n-2 and the inner loop runs from I plus 1 to n. So it's clearly big O of n square. Let us now talk about an efficient solution to count inversions in an array. The idea is based on merge sort. We divide the array into 2 halves. We sort these 2 halves recursively and then we merge these 2 halves. We do exactly what merge sort does. But with this merge sort operation, we also count inversions while we are sorting the array. We count inversions in the left half. We count inversions in the right half. And then when we are merging, we count inversions where one element is from the left half and the other element is from the right half. Let's understand this approach. Say you have an array from elements L to R. L is the starting index and R is the ending index. You compute the midpoint like you do in merge sort, L plus R by 2. After you compute the midpoint, every inversion which is there in this whole array can have 3 possibilities. So here we are considering inversion xy such that x is greater than y. The first possibility is both x and y lie in the first half. So this is the first half and this is the second half. So both x and y lie in the first half. That's one possibility. The second possibility is both x and y lie in the second half. And third possibility is x lie in the first half and y lie in the second half. Please note that it will be an inversion only when x lies in the first half, because x is a greater element, right? So that's why we have only 3 possibilities. Now please pause this video and try to write down a merge sort based function that counts inversions in the array. Here is basic idea for the recursive function. We compute the midpoint. We recursively call count inversion for left half from L to M. Then we recursively call count inversion from M plus 1 to R. These two functions not only count inversions, they also sort left and right halves. And we'll soon discuss what is the advantage of sorting while you are counting inversions. We'll discuss this when we will discuss this count and merge function in detail. That's a key function here. It merges two sorted arrays and it also counts inversion such that one element is in the left half and the other element is in the right half. This is also done by count and merge. So what are we doing here in this basic function skeleton? We are simply counting inversion in the left half, counting inversion in the right half, and we are counting inversions while we merge these two parts, right? And at the end, we simply returning the result. Now please pause this video and try to write down count and merge function. Also think of a reason how sorting left half and right half and then sorting the whole array helps us in efficiently counting inversions when we are merging the two sorted halves. Let us now talk about count and merge function. This function is very similar to merge function of merge sort. In fact, almost all the code is same except these few differences. Result is a variable which is used here, which is initialized as 0. This is where we update the result and this is where we return the result. Since we are returning an integer value, our return type is also different. It's instead of void, it's now int. These are the only changes. Otherwise, it's similar to merge function. We create two temporary arrays left and right. We copy the elements from L to M into left array. We copy the elements from M plus 1 to R into the right array. And then we begin this loop where we compare which element is smaller, left I or right j. If left I is smaller, we put left I in array k. Right? If right j is smaller, then we put right j into array k and we do j plus plus here, we do I plus plus here. In this case, when right element is smaller, we also update the result, right? That's what we are doing extra here. After that, this is again same as merge. If there are extra elements in the first array, you simply put those elements into array k and increment the corresponding indexes. If there are extra elements in the second array, you put those elements in the array k and increment the corresponding indexes. At the end, you simply return the result. Let's now see what happens with these lines. What is the significance of this particular line with this example? So let's do this one by one. We begin with I equal to 0 and j equal to 0 and k equal to L at this point. We compare array I and array j. Here array I is smaller, right? So we put array I here in array k, right? And move I to the next point. And when array I is smaller or same, when we are in this case, we do not update the result, right? We do update the result when we are in the other case. Let's now see what happens in this line. What is the significance of this particular expression? Let's understand this with an example. So we have, say, left array as this array and right array is this array. Left half is also sorted and right half is also sorted. N1 is 4, N2 is also 4. Number of elements in the left array and right array. And this is our original array ARR, right? And we are going to merge these one by one and going to write the elements in this array. So our I begins with 0 for the left array. Our j also begins with 0 for the right array. Our k begins with the first index of this array, right? Which is initialized as L here. Now we compare left I with array right j. So we compare 2 and 3 and we fall into this case, left I is more than equal to right of j. So what are we going to do? We are going to copy this element 2 here in our original array and we are going to move I hat here at this point. So I moves here at this point and now we also going to move k here at the next point. After that we run this iteration again and compare left I with right j, right? We compare 5 and 3 and this time right j is smaller. Right, so you fall into this else case and this time you are going to update the result. So what do? You simply copy right j into the array. So you copy 3 here, right? And you move ahead next in this particular array, right? So your j now is here. And what else you do is you update result equal to result plus n1 minus I. So what is your new result? Result equal to 0 plus, what is n1? n1 is 4 minus I. What is I? I is 1 here. So your result becomes 3. Now what is the significance of this particular line? See, you found an element in the right array which was 3, and this element was smaller than this element 5. So this element is going to be smaller than all the elements after this index I. It's going to be smaller than this, it's going to be smaller than this. So it's going to be smaller than 3 elements in the left array. What it means is, it's going to form an inversion with all the 3 elements. 5, 3 is an inversion, 8, 3 is an inversion, 11, 3 is an inversion. So we have 3 inversions because of this element being smaller. And that's the significance of this line. That's why we add n1 minus I. If we find an element in the right array which is smaller, then it's going to be smaller than all the elements from I to n1 minus I. So we add this expression to count the inversions found by right j and all the elements from left I to left n minus 1. Okay, so we again compare 5 and 6. And this time we find left is smaller, so we are not going to update the result, we are simply going to copy 5 here. Our I moves here. This time we again compare left I and right j, and we found that left I is greater than right j. Right? So what are we going to do? We are again going to update the result. So we are going to update the result as 3 plus n1 minus I. What is n1? n1 is 4, and what is I? I is right now 2. 4 minus 2, which is 3 plus 2, which is 5. And you can notice that this element forms inversion with 2 elements, and that's how we have added 2 here. And here you can notice also an advantage of sorting. What is the advantage we are getting with the sorted arrays? Whenever we see an element from the left array which is greater than an element on the right array, we are counting many inversions together in one go. Imagine arrays of size thousands each. So your total arrays of size 2000 and left and right are 1000 each. And in one go, you might count hundreds of inversions, because if this element is smaller, this is going to form an inversion with all the other elements in the left array. That's the advantage we are getting with the sorted arrays. Please note that with inversion count increment, we must also move this j here, right? J must move here, and we must copy 6 here at this particular position in the array. Now we are again going to compare left I and right j, and we find that left I is smaller. So we do not update the result, we simply copy it here and move ahead in the left array. Now we again compare left and right, and this time left is greater. So this 9 is going to form inversion with 1 element only. We can find it out also. Result equal to 5 plus, what is n1? n1 is 4, and what is I right now? I is 3. So we have only 1. So we have 6 as result now. And what are we going to do? We are going to put 9 here in the result array, and we are going to increment this here. And now again we are going to compare left I and right j. And this time left I is smaller, so we are simply going to put left I. And at this point, you come out of this loop because you have traversed all the elements in the left I. And what are you going to do now? You are going to come into this particular loop, going to copy 13 here, right? And at the end, you are going to return the result 6. So you have total 6 inversions such that one element is in the left array and the other element is in the right array. And the other inversions which were there within the left array and within the right array, we must have counted them when we recursively called for the left half and right half. So this is how this inversion count logic works using merge function. Let us now talk about time complexity of the solution. I think you must have guessed. It's simply doing merge sort work. So the time complexity is same as merge sort. It's big O of n log n. And it's just doing constant amount of extra work other than merge sort. So it's going to remain as big O of n log n. And since we are going to use the merge function which requires auxiliary space, we need big O of n auxiliary space to solve this problem.